So we just finished looking at the commutative and associative properties. And there's a third property that's usually linked with these two that definitely requires its own special attention. I don't think it's actually a property. The commutative property and the associative property are properties of particular operations. Right? You can look at two different substances and ask, well, what properties do these have? Right? So you can look at salt, and you can say, well, salt is white, it dissolves in water, it tastes salty, right? And you can look at something else. You can look at sugar and say, well, sugar is also white. Sugar dissolves in water. And sugar tastes sweet. And you can look at white latex paint and say, okay, well, latex paint is, if it's white, it's white. Latex paint does not dissolve in water. It's, well, I guess latex is water-based. Oil paint does not dissolve in water. I don't know what latex paint or oil paint tastes like, but I don't advise you to find out either. But paint has a different property of these two. These are both crystals, whereas paint is a liquid at room temperature. And when it turns into a solid, it doesn't have a crystalline structure. Right? Those are properties of each substance. When you look at the operation multiplication, it has this property. When you look at the operation division, it does not have this property. Right? The distributive property is not something that an operation has as a property. The distributive relationship describes how two different operations relate to each other. Now, trying to write this out in words is much more complicated than showing it symbolically. That's why it's almost always shown like this, right? What property is being shown here? What's even going on here? Well, it's all about just understanding what addition and multiplication are. So let's look at an example. 2 times 13. Most of my other examples so far I've been using one-digit numbers. I want the focus to be on the operation, not on the calculation of doing that operation. So branching out into two-digit numbers here, how do we find out what 2 times 13 is? Well, one way is to add up 13 plus 13. Right? 2 times 13 means you add up 13 2 times. So 3 plus 3 is 6, 10 plus 10 is 20. 6 and 20 we call 26. Well, we really just used the distributive property without making it explicit. Backing up a little bit into your fundamentals of how numbers work here, a 1 in front of a 3 really means 10 plus 3. Right? That's what a two-digit number means. You have 1 10 and 3 ones. Well, if I multiply that by 2, the 2 is being multiplied by 10 plus 3. I have 10 plus 3 2 times. I have 10 plus 3 plus 10 plus 3. This is all addition. Addition has the associative property. I don't have to associate the 3 with the 10. I could associate the 3 with the other 3. I don't have to associate this 10 with this 3. I can associate the 10 with the other 10. And that's how we do addition. 3 plus 3, I associate my 3's. And then 10 plus 10, I associate my 10's. I get 26. Well, this works whether I have 2 13's or 3 13's or 97 13's. 3 13's means I have 10 plus 3. 3 times, how many 3's is that? 3 3's. How many 10's is that? 3 10's. So there's my 9 more than 30, 39. Same thing if I show it this way. Now, if you're writing it this way, you might start to suspect, wait a minute, Professor Newman, you said addition was binary. You can only add 2 things at once. Now you're adding 3 things at once. What's going on? Well, we're really adding 6 things here, right? I have 10 and 3, and 10 and 3, and 10 and 3. That's 6 individual inputs that I'm going to add 2 at a time. 3 plus 3 is 6. Now I have one number here. 6 plus 3 is 9. Now I did that binary. Now I start over. 10 plus 10 is 20. There's a single addition. 20 plus 10 is 30. Now I'm doing that very quickly, 10, 20, 30, but I'm still only technically adding 2 values at a time. So 20 plus 10 is 30, and that 30 plus this 9 is 39. Right? Instead of writing 30 plus 9, I'm not carrying or anything. Even if I did carry, I'm still putting my 10's plus my 1's as a 2-digit number. Now, if I did only have 1-digit numbers, I wouldn't bother to distribute. Right? 3 plus 4 is 7. Now 2 times 7 is 14. No distribution necessary. I could distribute if I wanted to. I have 2 3 plus 4's, so that's 3 plus 4 and another 3 plus 4. Well, we usually just skip this step. I don't bother to write 3 plus 4 plus 3 plus 4. I'm just saying I have 2 3's and I have 2 4's. Making this little rainbow kind of takes the place of organizing my thoughts this way. 2 3's gives me 6. 2 4's gives me 8. And 6 plus 8 is 14. As opposed to 2 7's being 7 plus 7 is 14. Right? 7, 3 plus 4, and 7, 3 plus 4. If I just associate these to get 7, associate these to get 7, that's just as good, just as mathematically correct as if I associate my 2 3's and associate my 2 4's. No reason to distribute here. The reason why the distributive property is so important in this class is because we sometimes have variables. I can't just do the operation inside parentheses if I don't have all the information I need to carry out that operation. I know that 3 plus 4 is 7, so I can perform that operation. I don't know the value of x, so I don't know what the value of 4 more than x is. I can't do this operation, but what I can do is recognize 2x plus 4's means x plus 4 plus another x plus 4. I can recognize that I'm adding up 2 x's here. And I'm adding up 2 4's. And I know what 4 plus 4 is. That's 8. And now I'm done. I have simplified this expression because I no longer need parentheses. I've written a product 2 times a sum as a sum, 2x plus something else, 2x plus 8. Right? And in general, one of the rules of syntax for algebra is we don't like to have parentheses. For something to be fully simplified, we shouldn't need to use any grouping symbols in that expression. In general, as we get to more complicated expressions, that rule might change slightly. Now, because multiplication is commutative, typically we put this single factor on the left, but it could have gone either way. I could have written this exact same expression using the commutative property to put x plus 4 on the left and 2 on the right. I don't technically need that dot, but oops, I know it's not going to use just a dot. I could have written it as just x plus 4, 2. This is less common. We typically put the monomial in front of the binomial, um, just like we usually put the number in front of the variable, but both do mean the same thing. So we can look at something else. Come on, why aren't you changing for me? Here we go. Say y times x plus p. I don't know how many x plus p's I have, if it's 1 or 2 or 19 or 2/3. But I know that this principle of distribution will work the same way. Even if I use a different definition of multiplication, that's not just repeated counting, but that distribution also applies. Now, another point about syntax, when we have multiple variables within the same term, it's just nicer if they're in alphabetical order. And then we don't have to fret about whether xy is the same answer as yx. We will all put xy because that's alphabetical order. P comes before y in the alphabet. So this is the best possible answer, most simplified. Sometimes when we bring in other variables that aren't just Latin letters, it gets a little more complicated. So that's also correct. It's just this is a little bit nicer still. So it's important to recognize this is not a property of addition or a property of multiplication. It's just a statement about how multiplication relates to addition. Because multiplication is repeated addition, we can write it out this way. Even when we have something like this, we can't really add 4 to itself 2/3 of a time, but it does still repeat. I'm getting 2/3 of all of this, which means 2/3 of 4 and 2/3 of 7. And we'll get into fractions in a little while, but that's the relationship between multiplication and addition. Now, it doesn't work the other way. If I have 2 plus 3 times 5, I'm not distributing addition over multiplication. 3 times 5 means I'm adding 3 5s plus another 2 being added to that. The 2's not doubling the 3 and doubling the 5. It's not doubling anything. It's just 2 added to this product. Just like 3 times 5 divided by 6. This is not addition that's being done 3 times. 5 divided by 6 plus 5. Let me again. 5 divided by 6 plus 5 divided by 6 plus 5 divided by 6. There's something being multiplied by 3. I have whatever was in the parentheses here 3 times, whether I write it in fraction form or using the division symbol. There's no 3 5s, 3 6s. This is a different thing. This is not the distributive property because this was not addition. If I have 3 parentheses 5 minus 6, the fact that 5, let's make this a variable so I can't do it. I recognize minus means adding the opposite. And now it is distribution, right? 3 times 5, 15. 3 times the opposite of 6, x. So 3 times 6 is 18, but I want the opposite. Now for my final answer, plus negative does not look as nice as minus, so I'm going to write it as 15 minus 18x. Now, what if that initial number was a negative number? This had been a negative 3. Well, everything works the same, except that 3 is negative. So negative 3 times 5 is negative 15. Negative 3 times negative 6, the opposite of a negative is positive 18. So I would just have the opposite answer. But the fundamental principle is the same. Whether my monomial is negative or positive, it's still being distributed to each term here. It also doesn't matter how many terms I have here. If I have 3 times 5 minus 6x plus p plus 2, 3 times 5 is 15. 3 times negative 6 is negative 18 times x, negative 18x. 3 times p is 3p. And 3 times 2 is 6. But I'm not done. 15 is a whole number, no variable involved. 6 is an actual number, no variable involved. I can add 15 and 6. Let's see, 15, 16, 17, 18, 19, 20, 21. That's 21. But I can't subtract the 18x because I don't know if this is actually 18 or 18 dozen or 18 thirds or 180. I don't know the value of x, so I don't know the value of this term. Same thing with the value of p. So here's my answer. And of course, if I'd recognized that from the beginning, if I had seen 5 plus 2 is both whole numbers, 5 plus 2 is 7. 7 times 3 is 21. So when we can perform additions within the parentheses, that's generally a better way to do it. Then I have a single multiplication to do, 3 times 7 to get 21, instead of multiplying again, and then adding. All right, so there's our understanding of the distributive relationship between addition and multiplication.